Now today we are going to learn how to calculate in a more accurate manner. We know now we have laminar, can be turbulence, can be entry region, can be fully developed region. The H have different expressions. Let's deal with the most simple case. For laminar flow in fully developed region, how can we calculate this convection coefficient? It is 8.4. Let's pick a period of 2. And assume we already achieved the fully developed condition. And the tube it is a circular tube, has a radius of R0. And let's say we have the y-axis here is the radial axis, and we have along the tube length. For x-axis, we use it as a temperature value. So when the laminar flow achieve fully similar, has been fully developed both hydrodynamic and thermally, we know the velocity profile is parabolic, right? 0 because of no slip collision at the maximum at the end. If I say for a heating case here, what would be our temperature profile look like for a heating case? The surface temperature is larger. Here we have Ts, and where would we have our minimum temperature value? The middle is the center line. Something like this, right? This is our mean temperature, and the temperature increase as it closer to the surface temperature, because now we consider heating case. If it is cooling, surface temperature is at minimum, and the fluid is at high temperature. So it is not always the same. And we briefly mentioned it has a parabolic look-like profile, but not exactly same, because our maximum temperature is not always twice the mean temperature of the profile. And we define our convective heat flux H times. In external flow, we define H times the temperature difference between surface temperature and mean temperature. We know we have maximum. For heating case, that's the surface temperature. Mean temperature is what at the center line. Where is more or less can we locate the mean temperature of the fluid? Minimum here, maximum here. Where is our average temperature value? This is what we have for mean temperature. And this distance is more or less like for temperature increase from the minimum to our mean temperature, or decrease from the maximum surface temperature to mean temperature. It's more, let's just give an approximation as half radius, right? Assume it is linear, although it is not, but let's assume it is. Since the first class of second week, we learned for convection, which is a combination of conduction within a very, very thin thermal boundary layer and have advection outside. H times temperature difference, which can also be considered as the conduction within what we have in the thermal boundary layer. In this way, we have K, and for temperature, vary from T surface temperature to its mean value. The distance varies, is half the radius. By the first approximation, it's not exactly the same because temperature profile is not parabolic, not linear. But more or less, let's do this approximation. And in this way, a question, K should be the value for fluid or for the tube. Fluid, right. Not like Biot number. Biot number is K for the solid. Here K, we deal with the internal flow inside. Now in this way, we have temperature difference on both sides. And we have our convection coefficient. It's more or less like twice the thermal conductivity of the fluid over the radius. There is a half radius here, and the radius is half diameter. So this is force thermal conductivity of our fluid over the diameter of the tube. And its dimensionless counterpart, Nusselt number, defined as for Nusselt number, HL over K, right? For internal flow, characteristic length is always, for circular tubes, is the diameter of the tube over Kf, the thermal conductivity of the fluid, by definition. And if we substitute our approximation here, the H is more or less like 4 times thermal conductivity of the fluid over diameter. We have a constant value of Nusselt number, which is number 4 by approximation for laminar flow. This list is not applicable for all the cases. It must first, the approximation is valid for laminar flow and fully developed region. We will discuss what happened in entry region later. And we end up with a constant. Have we already talked about surface conditions? No. We just say it is a heating case, whether it is under constant heat flux or constant tube surface temperature. We don't care. So this is also independent of surface conditions. And we have nothing related with the Reynolds number and the Pareto number there. It's independent of the Reynolds number and the Pareto number. Just by approximation, based on our understanding of the convection, is equivalent to heat conduction within thin thermal boundary layer. We end up with a constant number of 4. The textbook solved a bunch of very complex differential equations and gives us exact value, but this value depends on some surface conditions. For constant heat flux, the book gives us exact value of Nusselt number equal 4.36 in fully developed region. And for constant surface temperature, the book solved the differential equation again and end up with a constant Nusselt number of 3.66. And they are different for these two thermal surface conditions, but just by what we have there is more or less the number of 4 here. we didn't solve complex differential equations, but just by approximation, we end up with a value very similar to the exact values. And why in the fully developed region, why the Nusselt number is constant? Yes, because once it reaches the fully developed smaller region, the H decrease first in entry region, now maintain constant. So we have constant Nusselt values in fully laminar flow, fully developed region. But things get complex when in the entry region, because in entry region, our H, the convection coefficient, varies and decrease along the length of the tube. The textbook provides two solutions for entry region, average Nusselt number in laminar flow entry region. The first one is a summary entry, it's termed as summary entry length solution. It has two possibilities. First one, you hit the tube after it already achieved the fully developed velocity profile. Right? You let the flow develop first, then hit it. And or it applies to flow with a very large Prandtl number, which means our summary entry length is much larger than hydrodynamic summary length. It's more or less we can consider the summary temperature profile developed with a fully developed velocity profile. The dashed lines gives us solution for high Prandtl number value. And it also plotted another solution called combined entry length, which means the fluid, the viscous boundary layer and the summary boundary layer is more or less developed at the same time. They are means our Prandtl number is at the order more or less like 1. It plots the solution for A, which we have Prandtl number equal 0.7. And that's 8.57. That's for summary entry solution with Prandtl number or combined entry length, but applies for Prandtl number larger than 5. For a Prandtl number larger than 0.1 and smaller than 5, more or less at the order of 1, we need to apply what we have for 8.58. That's super complex. But when with those two solutions are accurate with each other, with these 3%, when Prandtl number is larger than 5. So for water, for example, Prandtl number is 7.56. We can just use the summary entry region solution directly. And all the properties, those correlations, not necessary to memorize, they will all be provided in the formula sheet. They are plotted against some dimensional parameter termed as the great number here, as the ratio of the x is what we care about, the length of the tube over the diameter of the tube, then divided our Reynolds number and the Prandtl number. All the similar properties like K, alpha, viscosity, we should evaluate it at some, they call average mean temperature. Although average mean sounds to me are the same, but I cannot figure out anything better. Average mean temperature is not like film temperature. In external flows, film temperature is the average between surface temperature and the fluid temperature. But in internal flows, the average mean temperature here is the average value between the inlet mean temperature and the outlet mean temperature. Those are solutions tabulated for laminar entry region.